In the last class, what we had, we understood what is meant by a gray surface. We spoke about the universal relation that directional, spectral emissivity and absorptivities are always equal. Then we have seen that if the irradiation is diffuse, or if the surface is emitting radiation in a diffuse manner, that means epsilon lambda theta and alpha lambda theta both are independent of direction, that is theta. In that case, the spectral emissivities and absorptivities are going to be equal. We also have seen that for many of the engineering surfaces, the assumption that the surface is diffuse or the irradiation is diffuse, they are valid approximations. From the spectral values of emissivities and absorptivities, if you would like to make these two equal, then one of the two conditions must be satisfied. The restrictive condition, most restrictive condition, is if the emission is coming from a black body at the same temperature as that of the object. In that specific case, what we are going to have is epsilon would be equal to alpha. And there would be a second case, which is again an engineering surface approximation. If we see that the emission and the absorption are independent of wavelength, for that specific case, and for those surfaces which follow this restriction or this relation, they are known as gray bodies. So, for a gray body, the value of alpha will be equal to the value of epsilon. So, we understood the restrictions or the conditions inherent in these steps. Today, we are going to start with another concept, which is the concept of a view factor. We all can understand or appreciate that the total amount of radiation coming from an object is not going to incident on another object. How much of radiation coming from one object is going to incident on another object would depend, among other things, what is the distance between the two objects or the two surfaces, what are the relative orientations of these two. One surface can be directly on top of another, and then most of the radiation coming from surface 1 is going to be intercepted by surface 2. Now, if there is a slight offset, then not everything that is coming out of surface 1 is going to strike surface 2 directly. Similarly, if the distance between two surfaces, even though they are exactly on top of each other, if the distance increases, then less amount of radiation coming out of surface 1 is going to strike surface 2 directly. For example, if you think of a cylinder, and let us say that bottom surface, the circular surface, and the top circular surface, these are the two surfaces of interest to us. We would like to find out what is the amount of radiation exchange in between these two surfaces. Of course, if the length of the cylinder is higher, then less energy coming from surface 1 is going to strike surface 2. So, it is the orientation and the distance, these two are going to be important. Now, for discussion of view factor, we are going to assume that all the surfaces are diffuse emitters and diffuse reflectors. With that, we are going to define some concept known as view factor. It is a fraction of energy that is going to strike surface 2 coming from surface 1. So, surface 1 is going to emit some amount of energy into the hemispherical space surrounding it. Only a fraction of that energy is going to strike surface 2. So, view factor is the fraction of energy coming from surface 1 that is going to strike surface 2 directly. So, why directly? Because we are discounting the fact that there may be other surfaces present in the surrounding that may reflect part of the radiation coming from surface 2, coming from surface 1 and directing it to surface 2. So, we are not going to include those indirect radiation that surface 2 is going to receive from surface 1. It is only the direct radiation with which we are going to restrict ourselves. So, the view factor concept is straightforward. Its value is obviously going to be less than or equal to 1 And for that we are going to see, like, to find out the relation between view factors. Let's think of a differential area element dA1 and a differential area element dA2, which are parts of larger finite surfaces A1 and A2. If I join dA1 and dA2, and these are the normal area vectors n1 and n2, and they make an angle equal to theta 1 and theta 2 with this line joining dA1 and dA2. Both these surfaces are emitting irradiation I1 and I2 into the hemispherical space. We would like to find out what fraction of energy emitted by dA1 is going to be directly intercepted by the area differential area element dA2. So, I am trying to find out what's going to be F, that is the view factor between dA1 to dA2. So, that is the view factor or fraction of energy emitted by dA1 that is going to strike dA2 directly. Now, the amount of energy coming out of dA1 which is going to strike dA2 directly from the definition of intensity would simply be equal to I1 cos theta 1 d omega 1 2. The definition of solid angle and intensity tells us the amount of energy, or rather the flux, which is dq1 by dA1 is simply going to be the intensity, whatever be the angle between the normal area vector and the line joining these two, multiplied by d omega 1 2. D omega 1 2 is the solid angle subtended by dA2 on dA1. So, in order to find out what is going to be d omega 1 2, this is dA2. I have to first find its projection on the normal projection normal to the line joining dA1 and dA2. So, I have to find out what is going to be dA2, which is normal to this line, and then divide that by r square. That is the definition of solid angle. So, d omega 1 2 would simply be equal to dA2 cos theta 2 divided by r square. That is the definition of solid angle. So, the amount of energy that is going to strike 2 coming directly from 1 is going to be dA1 I1 cos theta 1 cos theta 2 r square and a dA2. Are we clear up to this point? Okay. I have just used the intensity definition, which is energy per unit area normal to the direction of propagation. So, which is dA1 cos theta 1 per unit solid angle. So, that is the definition of I intensity which I have used in this development, and dA2 would simply be the area perpendicular to the line joining the two divided by r square. So, the total amount of energy is simply going to be this one. Yes.
Won't it be dA2 sin theta?
No, it is going to be your area. You have to find the area vector makes an angle equal to theta 2. So, the same logic why dA1 should be multiplied by cos theta 1 to find out whatever be the area which is normal to the line joining the two. The same logic could be applied to dA2 as well to find out what is the area portion of area which is perpendicular, or projection of area perpendicular to the line which is like A1 to A2. So, now I would like to find out what is going to be the total amount of energy Q1 emitted by surface dA1 into a hemispherical space, because as I know my view factor would simply be equal to dQ1 by Q1. dQ1 is the amount of energy which strikes A2 dA2, and I would like to find out what is Q1, that is the total amount of radiative energy going into the hypothetical hemispherical space around dA1. So, this simply would be equal to whatever be the area, and as we have done before, over the angle from 0 to 2 pi and theta equals 0 to pi by 2, intensity cos theta 1 sin theta 1 d theta 1 d phi. This we have seen before. Now, I said that both these surfaces are diffuse reflectors and diffuse emitters. So, if I say it is a diffuse emitter, can any simplification be done about this expression, that q1 is this integration multiplied by dA1. If it is a diffuse emitter, then I is not going to depend on the directions. So, I1 is going to be a constant, and I can simply bring I1 outside of this integration sign. And we already know what is the result of this integration, which is simply equal to pi. So, I am going to write q1 is pi times I1 dA1. I would emphasize the significance of q1. It's the total amount of energy emitted by dA1 into a hemispherical space around it when its intensity is equal to I1. So, if I have to find out what is the view factor between A1 and dA1 and A2, I simply have to divide dq1 by q1. That would give me the fraction, which is the view factor. So, the view factor which is expressed, the elemental view factor between dA1 to dA2 would simply be equal to dq1 by q1, and this is cos theta 1 cos theta 2 dA2 by r square. That is the definition, that is the expression for view factor, which we are going to use subsequently in all our discussion. If one has to find out what is dA2 to dA1, would the view factor between two surfaces, if you know the view factor of one, would you be able to find out the view factor of the other? Are they going to be equal? If I have two surfaces and if I know the view factor from one to the other, is it going to be the same for the view factor from 2 to 1? That's the question which I am trying to solve. They obviously they may not be same, because if you have say if you are considering a large surface and a small this one, then whatever be the view factor for this coming from this one would obviously not be equal to the view factor of this which is coming from the other one. So, I would like to find out what is the relation between dF dA1 to dA2 and dA2 to dA1. In the same way that we have evaluated what is dF dA1 to dA2, the other view factor can easily be obtained simply by interchanging the subscripts, nothing else. So, what I have then is again cos theta 1 cos theta 2 dA1 by r square. That is going to be the view factor from A2 to A1, which simply gives us the relation which we are looking for, the relation of view factors 1 to 2 and 2 to 1. So, if I do that, it is simply going to be this is the relation which can be used if you know the area of the two surfaces which we are considering and the view factor of one to the other. This relation is known as the reciprocity relation. So, that is straightforward. Knowing the view factor of one, the view factor of the other can be calculated. Now, these view factors can also be integrated over the entire surface to find out not the elemental view factors, but the overall view factors, like what is the view factor of f A1 to A2 or f A2 to A1. So, if you do that, you would simply I will not do that over here, it is pretty straightforward. It is going to be f A1 to A2 would be equal to f A2 to A1. So, from the elemental view factor by integration, one can obtain the relation for finite areas, the reciprocity relation for the finite areas. So, that is I suppose there is no question up to this point. All of us understand how view factors are defined, how view factors between elemental areas are evaluated, and by integration one can obtain the same relation between finite surfaces. Now, there are certain properties of view factors which are going to be extremely important. Let us say we have an enclosure and all the surfaces this is the AI surface this is the AJ surface. All the surfaces are emitting radiation. In other words, all the surfaces are exchanging radiative energy with one another, and we would like to find out, let us say, how much of energy we have to supply to A1 AI to keep it at a constant temperature. At steady state, you understand that you have to supply some energy to some of the surfaces and extract some energy from some of the surfaces. Let us say if this surface is at 3000 degree Kelvin and this surface is at 500 degree Kelvin, and all the other surfaces are some temperatures in between, then obviously in order to maintain steady state, you would have to supply energy to the 3000 Kelvin surface and extract energy from the 500 Kelvin surface. So, that is going to be extremely important information while designing a furnace. If you would like to expose some surface, some material to high temperature, high heat flux, and you are going to place it on one side of the furnace, you would like to find out how much energy the surface of interest is going to receive, and in order to maintain certain temperatures at those positions, how much of energy you have to supply from outside in the form of flue gases or some sort of fuel. So, these view factors are going to play an extremely important role for calculations inside an enclosed surface, which is going to be our next topic and which we will cover in the next class. But the reason why we are studying view factor is to get the idea what is the relation in terms of radiation between two surfaces or more than two surfaces forming an enclosure. So, some of the properties of view factors are going to be extremely important. The first one we have already understood, which is reciprocity, which simply tells me that AI F AI to AJ would be equal to AJ F AJ to AI. Okay, that is a reciprocity relation which we have just derived for two surfaces, and this is just a general relation. The second one is summation. If you sum all the surfaces, the view factor from AI to AK, this sum would be equal to, if you find out what is the energy that is going to be received by all surfaces including itself forming an enclosure, it has to be equal to 1, because suppose surface AI emits some amount of radiation, that radiation is going to be taken up, part of that radiation is going to be taken up by all these surfaces including itself. AI may also receive some radiation which is being emitted by itself. So, if that is the case, then since view factor is a fraction, if I sum all of them together over all the surfaces forming the enclosure, that sum must be equal to 1. Clear? So, two relations clear. Now, when I say that surface AI is going to receive part of the radiation emitted by itself, it can only do so if the surface is concave. If the surface is a plane one or a convex one, then it is impossible for the surface to receive some amount of radiation which is being emitted by itself. Only if the surface is of this shape, then part of the radiation emitted by this zone is going to be absorbed by the other zone, in which case the view factor from one surface to itself will not be 0, but for a plane or a convex surface, the view factor to itself will be 0. So, you have some other relations, AI to AJ would be equal to 0 if surface plane or convex. It is not going to be equal to 0 if the surface is concave. So, these are the three relations which we will use, and the next part of this class is going to be, I am sorry, AI to AI would be 0 if the surface is plane, or it is not equal to 0 if the surface is concave. So, these are the three relations which we will subsequently use in the next part of the class, which is going to be tutorial 1 in the next class, to solve view factors of certain geometries. Now, let us say if you have n surfaces, okay, how many view factors are possible? If you have n surfaces forming an enclosure, how many view factors are possible? If you have one surface, if you have two surfaces, how many view factors are possible? If you have two surfaces, one's 4, because this from 1 to 2, from 1 to 1, from 2 to 1 and 2 to 2. If you have 3 surfaces, 9. So, if you have n such surfaces, number of possible view factors would be n square. All right. And so, if I have the view factor matrix, it is going to be equal to f11 up to f1n, f21 to f2n and fn1 to fnn. So, these many view factors one has to evaluate before he or she tries to solve the radiation problem. So, if you have a furnace containing 5 surfaces, then you have to know 25 view factors to start your calculation of how much energy you have to supply through one or more of the surfaces. Now, since we have certain relations, number of view factors that are to be independently evaluated must be less than n square. So, you would see what are the extra relations we have which would reduce the number of view factors that you must independently know to know all the n square such surfaces. Now, we have reciprocity. I would just write reciprocity relation, which would provide how many relations? For surface 1, how many relations, reciprocity relations are there? N minus 1. Surface 2, 1 is already counted. So, you are going to start with n, n minus 1, n minus 2, n minus 3 and so on. So, all the sum of all these relations are already there. So, reciprocity would give you n into n minus 1 by 2 such relations. Okay. So, you would have to independently evaluate n square minus n into n minus 1 by 2, that many relations. You are also going to have summation relations. How many summation relations for n surfaces you will have? For surface 1, you have just one. Okay, f1 plus f11, 1 2, 1 3, etc. would be equal to 1. N such surfaces, n number of relations. So, summation relation would give you n such relations. So, number of view factors that you have to independently evaluate would be n into n minus 1 by 2 minus n. If in addition you have we have specified that the surfaces are convex or plane, how many view factors would vanish? N number of view factors. If we mention that all the surfaces are either plane or convex, then n number of view factors will be equal to 0. So, you do not have to know n more number of view factors if the surface, the shape of the surface is specified. So, for that special case, what you have to find out it is n into n minus 3 by 2. These many view factors you have to know before you start your radiation calculations. So, these many view factors are needed. Now, when we have seen that view factors are evaluated by integrating over the surface, okay, taking into account the solid angle subtended by one onto the other. Now, these are complex relations and time consuming to evaluate. So, what we have is a series of charts and graphs which would give you the view factors between two surfaces of known shapes, rectangular, circular, etc., depending on what's the relative distance, what's the distance between the two, and what's their relative shape. So, from a large rectangle to a small rectangle, from a large circle to a small circle, as a function of the ratio of these two radii and as a function of the distance between the two. So, if you have a large plate and a small plate, obviously the view factor is going to depend on R1 and R2, or the ratio of R1 and R2. It is also going to depend on D if D is the distance between the two. So, all the figures, charts, etc., which are available will give you the view factors from one surface to another, provided all these dimensions are known to you. I will just give you some of the examples, and these are available in your text. You can take a look at it and find out the view factor for if the surfaces are known to you. So, what are the things if A1 to A2 would depend on? A1 is this surface, circular, A2 is another circular shaped object. L is the distance between the two. So, if A1 to A2 would depend on what are the physical things? It would definitely depend on R1, R2 and the distance between the two. Okay. So, these are the things on which your integration results would depend on. So, when you see the graph, it is L by R1 and R2 by L. Okay. So, if you know R1, R2 and L, you should be able to find out what is the view factor from 1 to 2. And if your f A1 to you should be able to read it from the graph. If A1 to A2, if A1 to A2 is known to you, would you be able to find out A2 to A1 simply using reciprocity relation? So, it is going to be A1 if yes, true. It's also going to depend on whether this is like this or they are situated directly on top of each other such that it's like this. So, the figure that I have given you is for the case where it's like this, one on directly on top of the other. If it is offset by a certain amount, there has to be some other relation which would give you the factor, the view factor A1 to A2.
It can be rotated also. Like
It can have theta, it can have phi. Agreed. So, for complex geometries, it would be very difficult to find out for irregular shapes to find out what is the view factor from 1 to 2. Okay. I would give you another example in which, even though suppose you know the view factor for this case from the chart, would you be, if this is shifted without, as you have said, making any angle in this direction, if it is just shifted, can I find out the view factor? Which brings me to the next part of my presentation, which is view factor algebra. But before we do the view factor algebra, let me give you another example of two surfaces. Let us say I have f and a small surface, elemental surface and a relatively large surface. So, this is A2 and this is dA1. dA1 is directly below this, it is like this, which basically tells you like if A2 is directly above dA1, it will have a different value of view factor, and L1, L2 etc., as well as the distance between the two are there. So, obviously, you can see that if dA1 to dA2 would depend on L1, it would depend on L2, and at the same time it will depend on D, right. You have similar such figures for two surfaces which are two surfaces which are connected to each other, which one is A2, the second is A1, and you have the width, this is L2, L1, one side is common. Okay. For such a case also, if A1 to A2 would depend on L1, L2 and W. Alright. So, there are several different types of view factor graphs which are available, which would help you to find out the view factors for many of the situations which we deal with, because you can directly see that this is a case of two furnace walls in contact with each other, isn't it? If you have a rectangular furnace and two sides of it, like they are going to make 90-degree angle, and its two rectangular surfaces in contact with each other. Now, if these two radii are equal and if you connect it with a third surface, then it is a cylindrical furnace. So, we are going to deal with those cases as well. Two circles, and the two circular areas are connected by another surface, are enclosed, the two surfaces are enclosed by another surface, which is just a cylinder. Okay. So, these are the things which we will do in the next class, but to answer your questions a bit in a bit more detail, there is something which is known as view factor algebra, which is very simple. Like most of the things in radiation, it's very simple. Let us say I have a surface which is dA1, and directly on top of it, this is the line which is directly on top of dA1, but there sits another area which is A2, which as we have seen is not on top of this, but it is slightly offset. Okay. I know that if an area is directly sitting on top of this one, what is the view factor from the chart, but this is not sitting directly on top of it, it is rather offset by certain amount. So, but I would still like to find out what is the view factor. The easy thing to do is think of this area as if I have, do I have the view factor from dA1 to the large surface? Yes, that is there, but I have to find out what is view factor from A1 to A2, f dA1 to A2. What I am let us say this A2 and the whole surface is A3, this surface, this part is A4 and this part is A5. So, what I can say is that A2 would be equal to the total area minus A4, which is this area, minus A5, which is this area. That should be equal to, I am sorry, this should be equal to A2. Are you with me or not? Should I repeat it? Okay. Let us find out what is area A2. Area A2 would be the whole area minus this area minus this area, but in that case I have subtracted this area twice. So, that has to be added, that small area which is this area has to be added, which gives me the total area A2. So, similarly, f dA1 to A2 would be equal to f dA1 to A3. Is it possible to find out f dA1 to A3? dA1 to the whole area, that is possible. Okay. dA1 to A4, dA1 to A4 would be this area, that is also sitting just on top of this one. Okay. So, dA1 to A4 would be possible. A5 is sitting again on top of dA1. So, this would be dA1 to A5. A6 is also sitting on dA1. So, this would be f dA1 to A6. So, this would be the unknown view factor dA1 to A2. I'll repeat it again. I know the view factor if it is situated like this, that is from the table. So, I have the view factor for the from here to the whole area to any part of this area as long as the corner point remains common in all cases. So, even if I consider about A3, which is the whole area, the corner point is here, A4, which is this area, the corner point is still here, A5 corner point same, or A6 corner point same. So, if I know the if I can express it as a sum, or I mean algebraic sum of different areas with the corner points being directly on top of dA1, then even though this is offset, that can be evaluated. So, there would be several variations of this approach which are known as view factor algebra.
So why are we taking A5 and A6?
How do you like to do that then? You have this surface which is offset. Okay. There may be other ways of doing it. I am not saying that this is the only way. You would like to find out the view factor of this area with respect to this one.
So we can extend this vertical distance.
Which one are this and this? I have to bring the corner point over here somehow, because that is what is known to me.
So this vertical distance is fixed.
The vertical distance, obviously, depending on the vertical distance, you are going to have different values of view factor. Okay. Two surfaces, if they are close to each other, then they have a view factor. If they are far apart, then the view factor would obviously decrease, because some of the radiation is going to go out in between the two surfaces. The remaining time that we have before we start our tutorial part of this class, I would like to introduce another concept which is known as radiosity, which is probably more important than the radiation exchange or emissive power of an object. Because we know that when we are thinking of an enclosure, there are several ways. If you are an observer standing just outside one such surface, what are you going to sense coming from the surface? If you are standing outside a surface, you are going to face the emission which is coming from the surface. And if it's a black body, its emissive power is going to be sigma T to the power 4, Ts to the power 4. If it's a non-black body, a real surface, its emissive power is simply going to be sigma epsilon Ts to the power 4. But is that the only one you are going to experience, or you are going to experience something else? Think of it. It is the surface you are talking about, you are very correct. The surface you are talking about is not only emitting something, it's also reflecting some radiation which is coming from some other sources. So, if you are an observer, you are not going to sense the emission only, you are also going to sense the reflection that's coming from the object. So, the sum of these two, the total amount of radiation you would sense being an observer situated just outside the surface, that is called radiosity. So, radiosity has two components, one emissive component that depends solely on the temperature of the surface whose radiosity we are measuring or whose radiosity we are trying to find out, and the second component which does not depend on the surface, it's whatever be the amount of irradiation on the surface and what is reflected from the surface. So, in other words, I should not say it does not depend on the surface, because it depends on one surface property which is reflectivity. How much, what fraction of the energy, or what is the energy that it is reflected. So, if we express radiosity by, let us say, J, which again is a spectral quantity, that means radiosity can have different values at different wavelengths, and so it is going to depend on whatever be the emission. So, it is going to have an emissive part and it is going to have a reflective part. So, if we think of the spectral radiosity of a surface, into an hemispherical space, the same way as we have done before, except intensity, which we so far know as emission intensity, is going to be replaced by E plus R, emission plus reflection. It is an intensity based considering both of them, emission as well as reflection, and then the rest of the things would remain the same, cos theta, sin theta, d theta, d phi. And since its amount of energy, amount of spectral energy that you are going to receive, what would be the, it's the amount of spectral energy flux. So, what would be the unit of this? The same as E or E lambda. So, it would be watt per meter square, and since it's spectral, there is going to be a micron as well. Okay. So, if we have to find out the total amount, not the spectral one, then it's 0 to whatever be the wavelength, in fact it should be infinity, and it should be j lambda, and this will have unit of watt per meter square. All right. So, we physically understand what is radiosity, and this is probably more important than just the emissive power of it alone. Okay. If you are standing in front of a mirror and the mirror is reflecting sun rays, the temperature of the mirror and the resulting emission is unimportant. It is the reflected portion which is going to give you the warmth or whatever. Okay. So, sometimes emission predominates, sometimes reflection predominates. One is a volumetric phenomena which is emission, the other is a surface phenomena which depends on the reflectivity. Fine. The last thing which we would theoretical thing which we are going to discuss in this class is blackbody radiation exchange. Let us say we have two black bodies, AI, which is at a temperature of Ti, that is the outward directed normal area vector, and this is the other area vector, and you have Aj, Tj, and so on. I would like to find out what is the total energy that is coming out of. Do not think about them as black bodies. Let's take them as real objects. I would like to find out what's the total amount of energy, not the spectral one, the total amount of energy that's coming out of surface 1. You are trying to measure what's the total amount of energy coming out of surface 1. So, what would that energy be? You as an observer are trying to find out the total amount of energy coming out of surface AI. So, which is the quantity that you would like to know? It is the radiosity. So, the amount of energy that comes out of surface I would be AI times Ji.
So, in the radiosity calculation, we are not taking the transmittance?
These surfaces are treated to be opaque, okay, so that you have zero transmittivity. AI Ji would be the total amount of energy that you are going to sense coming out of surface 1. What fraction, how much of this is going to strike surface 2? So, I simply have to multiply it with F AI to Aj. Similarly, if you are standing outside surface Aj, the amount of energy that you are going to sense which is coming from surface Aj would be Aj times J, radiosity of J. Agreed? That is the amount of energy which you are going to sense as if it is coming out of surface Aj. Fraction of it which is going to strike surface 2 or surface AI directly would be F Aj to AI. All right. So, the net radiative exchange between these two surfaces, if I call it as Qij, this would be equal to plus or minus. This is the amount of energy given by surface 1 which is intercepted by surface 2. That is the amount of energy given out by surface 2 intercepted by 1. So, if I would like to find out the net radiative heat exchange between surface 1 and 2, what is going to be here, plus or minus? Minus. All of us understand that this is what we gain, this is what we lose, and this is what we gain. So, in order to maintain surface AI at the same temperature, this amount of energy will either have to be supplied from outside or taken out from the surface. So, by reacting with another surface present around it, this much of energy will have to be added or subtracted, taken out from the surface. If in addition we impose the condition that these two surfaces are black bodies, then what is the relation, what is the simplification that you can make in this expression? Ji would be equal to, both of them are black bodies now. Previously they were real surfaces, now I am making the restriction that both are black body. What is going to happen to Ji? Come on, Ji is emission plus reflection. If it's a black body, there is no reflection, so it has to be equal to emission or emissive power of the black body. So your Ji would simply be equal to Ebi if the surface is a black body. There cannot be anything any reflection part of it. So your Qij would simply be equal to Ai Fij Ebi minus Aj Fji Ebj, right? The Jis are going to be replaced by Eb. Any other simplification? This is equal to this by reciprocity relation. All right. So if these two are equal by reciprocity relation, I am simply going to write Ai Fij Ebi minus Ebj. And what else can we say about Ebi? How do we express Ebi? Sigma t to the power 4, and obviously since it's black body, no question of an epsilon. So this would simply be equal to Ai Fij sigma Ti to the power 4 minus Tj to the power 4. So two black bodies interacting with each other in terms of radiation, the net amount of heat transfer between the two subsurfaces or objects will be given by this formula. In the next class, what we are going to do is we'll keep them as real surfaces, and instead of just two surfaces, we'll make the problem slightly more complicated but slightly more realistic, make them as enclosed area. So three surfaces or more than three surfaces making an enclosed area, and maybe none of the surfaces are black bodies. So how do we calculate the net radiation heat exchange? Because what we are finding out from here, this Qij, this as an engineer would be the most important thing for you to evaluate, the net amount of heat that you have to add or extract in order to maintain the steady state. So this is for a black body two surface, we will go for real bodies more than two surfaces. So that's the radiation network method which we will do in the next class. Just a quick problem, this I would solve so that I will discuss and solve, and this is about a cylindrical cavity, and these surfaces are well insulated, and what you have is this is A2 A1 and its temperature is also given as 1350 centigrade. The diameter is given 0.075 meters. The length of the cavity is 0.15 meter, the value of which is also given, and you have this cavity is open to a surrounding whose temperature is 300 Kelvin, and this surface which I am calling as A2, its temperature is 1650 degree centigrade. I would like you to be very careful about something, because I have seen these mistakes by many students. There is no place for centigrade in radiation. Okay. So whenever you see centigrade, make sure you have changed it to Kelvin. Okay. So don't make that mistake. Anyway, so I would like to find out what's the total amount of energy how much what is the power required, the thermal energy required to maintain the condition at this. That means A2 would be at 1650, A1 would be at 1350. This is open. So how do I find out the total amount of energy that has to be supplied to the cavity, to the cylindrical cavity, to maintain its temperature at the respective temperatures? So for that we have to find out, this is obvious, what is the total energy that is leaving this hypothetical surface A3 which is open. the total amount of energy that leaves through the hypothetical surface A3, if we can find out, that is the amount of energy I have to supply into the cavity. Now, all the surfaces can be assumed to be black bodies. Okay. All the surfaces are assumed to be black bodies, and we would like to find out the amount of heat. So, can anyone tell me what would be the expression for the amount of heat that needs to be supplied to surfaces 1 and 2? Understanding the fact that the heat is going to lose through the surface 3. We are going to lose heat through surface 3, and surface 3 is going to interact with 1 and with 2. Apart from that, A1 and A2 may interact with each other as well. Is that the complexity of the problem clear to you? A1 is going to interact with 3, 2 is going to interact with 3, and 1 and 2 are also going to interact with each other. I would like to find out this value of Q. What is going to be the value of Q? Let us first think of what is 2's interaction with 1. This is a black body, this is another black body. The way we have the formula that we have derived just few minutes back, it would simply give me, that is A1 F13, then I have sigma T1 to the power 4 minus T3 to the power 4. This is the formula which we have derived just before, that if two black bodies are there, then the net amount of heat exchange between the two surfaces would be simply this one. Which other surface we should consider? Between 2 and 3. So, 2 and 3 both are again black bodies. Are you all with me? If you need me to repeat anything, please tell me. Is this part clear to all of you? Why I am taking 1 and 3 in the relation between 1 and 3 as per our derivation a few minutes back. The second one is A2 F23 T sigma would be there, T2 to the power 4 minus T3 to the power 4. So, that is the net amount of heat you have to supply at 2 because of its interaction with surface 3. The significance of this one, the net amount of heat you have to supply to 2, since its temperature is more than 300, because of its radiative interaction with surface 3. This is the net amount of heat you have to supply at 1 due to its radiative interaction with surface 3. Since all these surfaces can be treated as black bodies as part of the problem, this is what we are going to have. Do I need to consider A1 and A2? A1 and A2 are definitely going to exchange some amount of energy since they are at different temperatures. But if I take this as the control volume, the interaction between 1 and 2 is confined within the control volume. So, I do not need to consider the interaction between the two when I am trying to find out how much amount of energy I have to add from outside to the control volume. The amount of energy that I have to add from outside to the control volume must be equal to the amount of energy that is leaving the control volume, and definitely the interaction between 1 and 2 is not leaving the control volume. So, these two terms would be sufficient to calculate the total amount of energy that I need to add to the control volume, which in this case is the cavity. Is this part clear to all of you? Now, I can evaluate F13, and once F13 is calculated, F23 can be calculated. F13 value of which would be probably given to you, you would be able to read it from the chart, and F13, F23 would be obtained from reciprocity and summation relations. For example, what you are going to have is the value of F23 would be known to you. Once the value of F23 is known to you, then F21 plus F22 plus F23 would be equal to 1, right. In this case, F22 would be equal to 0 or not? F22 is a plane surface, so it would be equal to 0. So, you would be able to calculate what is F21, F2 to F1, and since you know F21, F12 can be calculated using reciprocity relation, all right, and F1 to F2, if you know F12, you have to find out F13. If F12 is known to you, what is F13? 1 to 2. If 1 to 2 is known to you, you like to find out here F1 to 3. What's the relation between F12 and F13? F11 is not equal to 0. F11 is a concave surface. F1 is a concave surface. A1 is a concave surface. So that you do not know about what is F11, but F12 is known to you. You would like to find out F13. How do you do that? It's a cylindrical cavity. What does symmetry tell you? Symmetry tells you, you know that F12 plus F13 plus F11 is equal to 1. You have evaluated 1, 2. Pardon me? F12 would be equal to F13 by symmetry. Okay, a cylinder from the inside surface to the top and inside surface to the bottom. It's symmetrical. All right. So F13 would be known from here. So when you substitute the values of A1, A2, sigma, T1, etc., the value of Q would be equal to 1844 watt. So what we are seeing here is the interaction of these two surfaces with outside. Some energy is going to leave. I evaluate that energy using the relation between black bodies, interaction between black bodies. Some amount of energy is going from 1 to 3. I use the same one, putting the proper value of the view factor. The interaction between these two is unimportant as far as amount of energy added from outside is concerned. I use this relation. If 23 is from the chart, if 13 is from summation, reciprocity and similarity. Okay, that's how you evaluate these things. So that's the end of about class about view factors, radiosity, and in the next class we are going to start with network method for solving radiations from real surfaces in an enclosure. Thank you.